lesson 117 is really just an extension of lesson 113. So this is about direct variation squared and indirect or inverse variation squared. So if you look at the very first statement, it says the distance required to stop is directly proportional to the square of the velocity. So this goes back to the whole idea of, as soon as you guys learn how to drive, one thing you absolutely have to learn is that the faster you're going, the longer it takes you to stop. And that's why it's dangerous to speed, especially in residential areas, because if someone runs out in front of your car, if you're going more than 30 miles an hour, it's going to take longer to stop that vehicle. If you're going 25, it'll be even faster to stop than if you're going 30. So I've written that equation for you. D equals K times V squared. So how about the price of a diamond varies directly as the square of its weight? Well, we'll say P is for price, okay, equals some constant times the weight squared. Okay, we measure diamond weight in carats, but we can just use W for weight. And now let's look at the indirect variation problems. It says the weight varies inversely with the square of the distance to the center of the earth. So the further you are from the distance, in terms of the distance of the center of the earth, the lighter your weight. So W equals K over D squared. How about the strength of the field is inversely proportional to the cube of the radius? Okay, so we're going to just use S for strength equals our constant divided by the cube of the radius, not the square, so it's going to be R cubed. Okay, so you can do any problem that is similar to that using that same idea that you have a constant divided by something else. So let's look at the first example. Actually, that one you already have the formula for up there. So I'm going to go ahead and I'm going to do example 2 for you, and then we can go over the others together in class. So it says the distance a body falls, and that doesn't mean a human body, it just means an object or something like that. It varies directly as the square of the time that it falls. So let's start off by just writing that much. So the distance a body falls varies directly. So we have our constant times something else as the time that it falls, the square of the time that it falls. So D equals KT squared. Okay, so if it falls 144 feet, that's our distance. In 3 seconds. So our time is 3. So K times 9. Then the question is, how far will it fall in 10 seconds? So let's find what K is first. So when we divide both sides by 9, we find that K equals 16. So the question is, how far will it fall in 10 seconds? So D equals 16 times 100, because 10 squared is 100. So 1,600 feet is how far it will fall. I believe that you guys can finish numbers 1, 3, and 4. Lesson 118 is about completing the square. So completing the square is a method we use in order to solve quadratic equations that aren't simple to solve. So let's start off by reviewing how we solve basic things like x squared equals 3. Well, we can take the square root of both sides and we find that x equals plus or minus the square root of 3. If we add 1 to x, the procedure is still the same. We have to take the square root of both sides. So we find that x plus 1 equals plus or minus the square root of 3. So then x equals negative 1 plus or minus the square root of 3. Because we had to take this plus 1, we had to bring that over by subtracting 1 from both sides. So negative 1 plus the square root of 3 and negative 1 minus the square root of 3. But we can just leave it like that. So I wanted to show you how to complete the square using an equation that you could solve without completing the square. But I feel like it gives you a better idea of how it works if you see it done this way as well as in the method of completing the square. So it's pretty easy to solve this. We know that we have an x in both spots. They're both going to be addition because we have a plus here at the end. And 5 times 2 is 10, and 5 plus 2 is 7. So we know those are our factors, 5 and 2. But let's say that it wasn't so simple and we didn't know what our answer was going to be. So if we had the equation was given to us in this form, the first thing we'd want to do is to write the equation in descending order of the variable. X squared plus 7x equals, minus 10 equals 0. All right, the next step would be to move the constant term to the right side of the equation. So remember, our constant is the number that doesn't have a variable with it. So we're going to add 10 to both sides, and we end up with, that should be a plus 10, and so now we should be subtracting 10 from both sides. Sorry about that. All right, so now we have x squared plus 7x, and I'm going to leave some space there, and you'll see why later, equals negative 10, which is, of course, what we started with. But I just want to show you how we do all the steps. So the next step would be to divide the coefficient of the x term by 2, square it, and add it to both sides of the equation. Well, what is the coefficient on our x term? It's that 7. So we're not going to divide it by 2 and make it 3.5 and then have to square that. The best thing to do is to keep that number as an improper fraction. So 7 over 2, okay, is that coefficient divided by 2. And if we square it, we get 49 over 4. And what we're going to do is we're going to take that and we're going to add that to both sides of our equation, 49 over 4. Okay, so now we have x squared plus 7x plus 49 over 4 equals, well, let's just write this as 49 over 4 minus 40 over 4. I just changed the 10. I multiplied it by 4 over 4. All right, so now what we have on the left is a perfect square. Okay, so we can simply write it as x plus 49 over 4, not 49 over 4, 7 over 4, over 2, not 7 over 4, 7 over 2 quantity squared equals 9 over 4. Okay? So what I did was I took the square root of this, and that goes here. And it becomes a perfect square. So now we can take the square root of both sides. And when we do that, we get x plus 7 over 2 equals plus or minus 3 over 2. Because both of those numbers are perfect squares. So now when we subtract 7 over 2 from both sides, we get x equals negative 7 over 2 plus 3 over 2 and negative 7 over 2 minus 3 over 2. So x equals 4 over 2, which is 2, and negative 10 over 2, which is negative 5. Okay, which is the exact same thing. Whoops. That should have been negative 4 over 2 and negative 2, which is the exact same thing we got here. So in this equation, we got x equals negative 5 and negative 2. All right, so we didn't have to use completing the square for that problem, but there are problems for which we do need to use completing the square. And you'll find out in the next lesson, we can actually also use the quadratic formula to solve those problems. But let's go ahead and do the example I have with my explanation portion on page 68 of your notes. So I have this example, x squared plus 6 equals negative 10x. All right, what we have to do is we have to bring that negative 10x over, so let's add 10x to both sides. And we have x squared plus 10x plus 6 equals 0. Okay, at this point we need to move our constant over. So we have x squared plus 10x equals negative 6. Well, our next step is step number 3, divide the coefficient of the x term by 2, square it, and add that to both sides. So we need to add 25 to both sides. So now we can simplify this as a perfect square into x plus 5 squared equals 19. Now we need to take the square root of both sides, and we get x plus 5 equals plus or minus the square root of 19. So x equals 5 plus the square root of 19 and negative 5 minus the square root of 19. Make note that is a negative 5. I would like for you to try to use the completing the square to solve the rest of the problems, so this video doesn't go too long, and we'll definitely spend a good bit of time on this. Lesson 119 uses something called the quadratic formula in order to solve equations. If you look on page 501, there's a proof there showing where they get the quadratic formula from. It actually comes from a basically setting up an equation such as this, ax squared plus bx plus c. All right, and using this using completion of the square with this equation in order to come up with this equation. All right, so the quadratic formula is a formula that you're going to have to memorize. The opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, and in that equation, a represents the coefficient on the x term. So that's why I wrote that like so. B represents the coefficient, A is the coefficient on the x squared term, B is the coefficient on the x term, and C is the constant. Okay, so you have to know where to get your A, B, and C when you're plugging everything into this formula. So when you are solving quadratic formula problems, what you want to make sure you do is start off by writing x equals the opposite of b plus or minus b squared minus 4ac all over 2a. All right, so let's look at our very first one. We have this equation, x squared plus 3 equals negative 5x. All right, first step, write it in descending order of the variable. So we write it as x squared plus 5x plus 3 equals 0. Okay, so A is what? A is 1, B is 5, and C is 3. And even though I have it written up above, I'm still going to write the quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, and now we can start substituting our a, b, and c. So x equals the opposite of b, which is negative 5, plus or minus b squared minus 4 times a times c all over 2 times a. And now you just plug and chug. Plus or minus the square root of 25 minus 12 over 2. So x equals negative 5 plus or minus the square root of 13 over 2. And that's as simple as we can make it. We can't simplify any further. If we could, we would. Let's do one more of those as an example. X squared plus 1 equals 3x. So we need to bring that over, and we get x squared minus 3x plus 1. What is our A? It's 1 again. B, negative 3, and C is 1. Okay, so let's go ahead and put our quadratic formula. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Now we can plug in. So what's the opposite of negative 3? Positive 3. Plus or minus negative 3 squared minus 4 times 1 times 1 all over 2 times 1. I'm just going to put 2. So x equals 3 plus or minus the square root of 9 minus 4 over 2. And at this point, we cannot simplify it anymore. So we're just going to leave it like that. Please try to complete the rest of it.
An ecologist surveys the age of about 100 trees in a local forest. He uses a box and whisker plot to map his data, shown below. What is the range of tree ages that he surveyed? what is the median age of a tree in the forest? So first of all, let's make sure we understand what this box and whiskers plot is even about. This is really a way of seeing the spread of all of the different data points, which are the age of the trees, and to also give other information like what is the median and where do most of the ages of the trees sit. So this whisker part, so you can see this black part is a whisker, this is the box, and then this is another whisker right over here. The whiskers tell us essentially the spread of all of the data. So it says the lowest data point in this sample is an 8-year-old tree. I'm assuming that this axis down here is in years. And it says that the oldest tree right over here is 50 years. So if we want the range, and when we think of range in a statistics point of view, we're thinking of the highest data point minus the lowest data point. So it's going to be 50 minus 8. So we have a range of 42. So that's what the whiskers tell us. It tells us that everything falls between 8 and 50 years, including 8 years and 50 years. Now what the box does, the box starts at, well, let me explain it to you this way. This line right over here, this is the median. This right over here is the median. And so half of the ages are going to be less than this median. We see right over here the median is 21. So this box and whiskers plot tells us that half of the ages of the trees are less than 21 and half are older than 21. And then these endpoints right over here, these are the medians for each of those sections. So this is the median for all of the trees that are less than the real median or less than the main median. So this is the middle of all of the ages of trees that are less than 21. This is the middle age for all of the trees that are greater than 21 or older than 21. And so these essentially are we're actually splitting all of the data into 4 groups. This we would call the first quartile. So I'll call it Q1 for first quartile. Maybe I'll do 1Q. This is the first quartile. Roughly a fourth of the trees, because the way you calculate it, sometimes a tree ends up in one point or another. About a fourth of the trees end up here. A fourth of the trees are between 14 and 21. A fourth are between 21 and it looks like 33. And then a fourth are in this quartile. So we call this the first quartile, the second quartile, the third quartile, and the fourth quartile. So to answer the question, we already did the range. There's a 42-year spread between the oldest and the youngest tree. And then the median age of a tree in the forest is at 21. So even though you might have trees that are as old as 50, the median of the forest is actually closer to the lower end of our entire spectrum of all of the ages. So if you view median as your central tendency measurement, it's only at 21 years. And you can even see it's closer to the left of the box and closer to the left, the end of the left whisker than the end of the right whisker.
What's up, everyone, and welcome to this lesson on box and whisker plots. Now, from your experiences as a math student, I'm sure that you've come across different methods of visually representing data. Pie charts, bar graphs, and scatter plots are a few examples of these tools. Box and whisker plots are another method of visualizing data to help us to make sense of it, and that is what this lesson is going to focus on. So again, a box and whisker plot is just a tool that's going to help us to analyze data. So first, we need some data. So let's look at Jordan, a JV basketball player who was just called up to varsity for the last 7 games of the season. So Jordan's using this chart to keep track of the number of points he scores for each of these 7 games. Now we can use this performance data to create a box and whisker plot that will help us to evaluate Jordan's performance over this 7-game span. Now our first step is to take those numbers and rearrange them in order from least to greatest. Now the first piece of information we can get from this data is what's called the upper and lower extremes. This represents the highest and lowest value in the data set. In this case, the upper extreme is 32 and the lower extreme is 5. The next piece of information that we need is the median. Now we know that the median is the middle of the data set, so I work from the outside in until I get to the middle value. In this case, 17 is the median. And the final piece of information that I need is what's called the upper and lower quartiles. Now we can think of this as splitting the data set at the median into an upper and lower regions. Now, the upper quartile is just the median of that upper region of three numbers, which we know is 20, and the lower quartile is the median of that lower region of those three numbers, which we know is 10. So we can say that the upper quartile is 20 and the lower quartile is 10. And now we have all the information that we need to construct our box and whisker plot. So we're going to start with a number line that fits our data. And we have to mark where our upper and lower extremes are at 5 and 32, as well as our median value at 17 and the values of the upper and lower quartiles, in this example at 10 and 20. Now imagine taking these points and elevating them above the number line. Our first step is to construct two vertical lines through the upper and lower quartiles and use these lines to construct a rectangular box that encloses the median point. And through that median point, we construct a vertical line. This represents the box in our box and whisker plot. And the final step is to draw horizontal lines that connect the upper quartile to the upper extreme and the lower quartile to the lower extreme. And notice that the graph itself is broken up into 4 different quadrants, each representing 25% of the whole. Now what you're probably thinking is, how can we use this graph to evaluate Jordan's basketball performance? Now, for example, by looking at the extremes, we could see that it's probably unrealistic to expect Jordan in an average game to score anything near his high of 32 points or his low of 5 points. Now, based on those extremes, you may think that Jordan is an inconsistent player. But if we look at the area inside the box, this is called the interquartile range, we can say that in an average game, Jordan will score between 10 and 20 points. And a coach can use this information to determine whether or not Jordan belongs in the starting lineup or on the bench.
Come on!
He can also use the box and whisker plot to compare Jordan's performance with the performance of other players. So let's extend this understanding to a real-world example. We're going to join Jess, who owns her own coffee shop, and she's keeping data on the number of espressos that she makes per day. So remember that our first step is to rearrange the values in order from least to greatest. And now we're ready to get the information that we need. So first we'll start with the extremes, the upper extreme at 96, the lower extreme at 32. Now for the median, again, moving outside in to find the middle value, we have two numbers, 51 and 59. So we just have to add them up and divide that sum by 2. So 110 divided by 2 is equal to 55, which is the median for this example. Now notice that the median is in between 51 and 59. So when I split my numbers up, I have to kind of draw a line in between those two values. Now to find the upper quartile, I find the median of those upper values, that's 65. And to find the lower quartile, I do the same thing for the lower values, in this case 44. So now I have the information that I need and I can construct my box and whisker plot. So as always, the first step is to construct a number line that fits our data. So we'll start with points that are upper and lower quartiles at 65 and 44. And then we'll construct a point for the median at 55. And we'll use these points to construct our box. So again, vertical lines through the quartiles, construct your rectangle, and then draw another vertical line through the median. Then we're going to plot points at the two extremes at 32 the lower extreme, 96 the upper extreme. Then just construct your horizontal lines, and the box and whisker plot is complete, and now you're ready to visually analyze your data.